I've been asked to solve z raised to the 8th power minus 1 equals 0. And I always interpret the instruction solve as find all solutions. So I'm thinking about complex numbers, real numbers. And since that's an 8th degree polynomial, I think I should have 8 complex solutions. So I'm going to actually imagine this is the equation z to the 8th equals 1. And then my 8 solutions are the complex 8th roots of 1. I'm going to start by writing 1 down in its polar form. Well, the number 1 unit to the right of the origin, so r is 1, times cosine of 0 plus I sine of 0. All right, so there's my value of r, and there's my value of theta. So I'm supposed to have 8 8th roots of 1. Demoivre's theorem for finding roots says they all have a modulus that is the nth root of that one. So the nth root of 1 is 1, so all of these are going to have a r value of 1, so I'm not even going to write that down. Each one of these will be cosine plus I sine of some number. Cosine plus I sine of some number, and I just keep writing them down in that way. And so I need to figure out what the angles are, but I'm going to go on and just make it easy on myself and write down this repetitive part, and then I'll just be filling in an angle in 2 places for each of these 8th roots. All right, my original angle is 0. The first angle here, well, that's supposed to be theta over 8 for us, theta over n, so that's going to be 0. Well, that should not be too surprising. If I plug a 1 in there, 1 to the 8th is 1 minus 1, 0. So my number itself is one of my nth roots. I find each successive angle by taking 2 pi and dividing by n. So that for us, that's 2 pi over 8 is pi over 4. So now I just repeatedly add pi over 4. And in my head, what I'm really doing is counting by pi fourths and reducing some of the fractions. But I suppose I could also be thinking visually, which I'll show you in a minute. My roots here are all equally spaced by that pi over 4. So I'm getting these values around the outside, just equal divisions of a unit circle by 45-degree angle. So pi fourths, pi halves, 3 pi fourths, pi, 5 pi fourths, 3 pi halves, and 7 pi over 4. These values are not particularly hard to write down in their rectangular form either. We could just imagine thinking about evaluating the trig functions, but instead I'm going to look at that diagram. The first one is just the number 1. This spot here, well, that's root 2 over 2 plus root 2 over 2i. Just thinking about where that point on my unit circle is, right? With an x and a y, that becoming a real part and an imaginary part. Now, if you prefer, cosine pi fourths is root 2 over 2. And the sine pi fourths is also root 2 over 2. And now I can just kind of go around my unit circle, writing down these points in their rectangular form. And not a particularly difficult process. Maybe we could consider it a tad tedious, but the next one up is I. And then I have minus root 2 over 2 plus positive root 2 over 2i. I'm down here at pi where I just have the real number minus 1. Minus root 2 over 2 minus root 2 over 2i. Straight down here at minus I, and then finally positive root 2 over 2 minus root 2 over 2i. And now I found all of the 8th roots of 1. Oh, if you think about roots of 1, one of them is always 1 and the rest of them are equally spaced around just by dividing 2 pi by n. And sometimes you'll hear people refer to these as roots of unity, because 1 is the multiplicative unit. So these are the 8th roots of unity.